In our physics class, we were asked to replicate one of two experiments that Galileo performed, his incline plane experiment or the pendulum experiment. We chose the incline plane. In this video, we will explain what Galileo did, what he learned from it, how we replicated the experiment, how similar or different our results were from Galileo, and what we can conclude from that. Our objective in this experiment was to prove that the distance traveled by a uniformly accelerated object is proportional to the time it took to travel squared.
Galileo was an Italian astronomer, physicist, engineer, philosopher, and mathematician. He was born on February 15, 1564, and passed away on January 8, 1642, due to heart palpitations. Galileo improved Hans Lippershey's telescope. The improvements he made on the telescope helped us view things in a vastly different way. His improvements showed that Jupiter has 4 of the moons that were eventually named the Galilean moons. He also proved that Venus undergoes phases like the Earth's moon, but Venus can only undergo those phases if it rotates around the sun. So if Jupiter has 4 moons and Venus goes through phases like the Earth's moon, how could Earth be the center of the universe? This led to Galileo's discovery that the Earth is not the center of the universe like the church had thought. Later in his life, the church had him sent to jail for suspiciousness of heresy, and he dies in jail. He also came up with the idea of inventing the 3-power spyglass through his telescope studies. We recreated his experiment of the inclined plane, where he found that if you roll a ball down an inclined plane at different angles, he could make statements about free-falling bodies undergoing the force of gravity.
Our apparatus included a ramp made out of a 1-meter-long piece of plywood inclined by a separate 8-inch piece. Our water clock was an emptied 2-liter bottle with a drain hose through the cap. We cut the bottom off and used as a collection cup for water for the experiment. The top left picture shows how we marked the starting position for the marble on the ramp every 25 centimeters. The picture on the top right shows the collection cup we used for the experiment. The bottom 2 pictures show how we fed a hose through the cap of the 2-liter bottle and secured it with hot glue. Using a ring stand, we secured the bottle and put the collection cup directly under the cap. With a finger over the end of the drain hose, we filled the clock with 500 milliliters of water. We then would release the marble of the predetermined location of the ramp while simultaneously letting the water flow by removing the finger off the hose. As soon as the marble reached the end of the ramp, we cut the flow of water. To find the relationship between the water and the time it took for the marble to reach the end of the ramp, we found the mass of the water of the collection cup minus the mass of the dry collection cup. We repeated these steps 5 times for 4 different locations on the ramp and recorded the data. By plotting the data and finding a line of best fit, we could see the relationship between the distance and the time it took for the marble to reach the end of the ramp.
Possible errors that could have happened during our experiment was the wood not being smooth enough, leading the marble to go down a bumpy path, the marble not being completely circular due to falling off of the surface and falling on the ground, the circular ball not going down a straight path due to us not having a groove down the wood that it allows it to keep going down a straight path. Measurements could be off on the wooden path due to incorrect readings of the meter stick, and start and stop times could be off due to the cramps that Justin had in his hand.
After compiling our data, I created this table displaying the values of water that poured out of our water clock in relation to how far the ball rolled down the ramp. As you can see, the amount of water decreased as the length of the ball rolled down the ramp decreased. In this case, we can infer that the mass of water at the end of each trial is directly proportional to the time elapsed, as we cannot use modern stopwatches. Next, I averaged the trials for each length and graphed that versus the distance traveled by the ball. The mass of the water is on the x-axis because it is our substitute for time. We have it labeled in grams. On the y-axis is our distance, which we measured in meters. Then we added a trend line in Excel so we could find out what type of function this was and how the two variables were related to each other. We had similar r-squared values for a few different trend lines, but the polynomial was the best with an r-squared value of 1. From this, we can infer that the distance is proportional to a squared value of the time. From this experiment, we can conclude that Galileo was correct in his discovery that distance is proportional to time squared. Essentially, if you doubled the amount of time the ball rolled, then it would travel 4 times as fast. This later helped him determine the value of the gravitational acceleration, which is denoted by the symbol g and is 9.81 meters per second squared. The discovery of the gravitational acceleration constant allowed other scientists after Galileo, including Isaac Newton and Albert Einstein, to further develop his theories and their own.